Welcome back. Let's recall the very important equation we developed last time. The equation is work is equal to integral P dV from V1 to V2, where P is pressure, V is volume, V1 is initial volume, and V2 is final volume. So it is really nice to have this equation. However, how do we start from this equation to do the calculation? Integration is always difficult, so we need to find a way to solve this integration. In other words, how do we solve this equation? We have two ways. The first way to solve it is by graphic analysis. The second way to solve this equation is analytical method. Analytical method is just to solve this equation and find equation. That's what you did in your calculus class. Okay, so we're going to do the first one, the graphic analysis. How do we analyze this equation? W is equal to integral v1 to v2 pdv. The first method is graphic analysis. Okay, so first of all, let's recall the diagram, pressure versus volume, pressure versus volume. And we said it's always one single curve. And now I tell you, this is my initial, this is my final. Can you tell me what kind of process is this? Is this an expansion process or compression process? 1 to 2, what is the direction of 1 to 2? 1 to 2 is going to the right. So that means my volume is becoming bigger. That means my 1 to 2 must be an expansion process. We're going to use the expansion process as one example. Okay, so the equation we have is work is equal to integral P dV from V1 to V2. Let's find V1 and V2 on this diagram. V1 must be the x-coordinate of point number 1, and V2 must be the x-coordinate of point number 2, V1 to V2. Okay, so now let's take a look. What is pressure on my diagram? Pressure is height on my diagram. What is volume on my diagram? Volume is the length of on my diagram. So pressure multiplied by volume, what is that on the diagram? Height multiplied by length. What is height multiplied by length? That is area. So work is actually area under the curve on a diagram. The area under the curve between V1 and V2 is equal to W. So this is the first way to analyze the equation. All right. Okay. Two things to point it out. First of all, area under the curve 1 to 2 is equal to work. And if we want to be more accurate, we should add absolute sign, the absolute value of work, because area is always positive, and work, like we said, can be positive and can also be negative. So to be more accurate, we need to add an absolute sign. Second thing, different gases have different curves. So for example, the curve for oxygen may look slightly different from the curve of nitrogen. It depends on what kind of gas you have. Okay, so that is our first method to analyze the equation. It's called graphic analysis. The good thing about this method is you can actually visualize the work because work is equal to area under the curve. So the good thing about this method is you can visualize where work is. What's the downside of this method? I can visualize it, but is there any way I can calculate the work? Or can I calculate the area under the curve? That's not possible from this method. Why? Because this is an irregular shape. There's no way I can easily find out the area. So that is the downside. I can visualize it, but I cannot calculate it. And that's why we need to use the second method, which is the analytical method. Analytical method. We start from this equation. Work is equal to integral P dV from V1 to V2. And then, like everything on the XY diagram, the curve can be written into this equation. P times V with the index of n is equal to constant. This is the equation of this line, just like y is equal to ax plus b is a straight line. This curve can be written into this equation. P is pressure, V is volume, index n depends on what kind of gas you have, and is equal to constant. Okay, let me make a note here. N, the index, depends on the gas. Different gases have different values for n. Okay, so now let's copy down this equation. PV with index of n is equal to constant. Let's combine those two equations together and see if we can solve the equation. Okay, so first of all, W is equal to integral V1 to V2 P dV. Can we rewrite pressure from this equation? Yes, we can. Pressure can be rewritten to constant divided by V with the index of n. So now what we can do is to plug it in back into here. Rewrite pressure. Pressure can be rewritten to constant over V with the index of n. Okay, so now let's continue. Let's continue. Let's continue. What's going to happen? Let's continue. W is equal to, what can I do to this constant? If it is a constant, I can pull it out. If I pull it out, it's going to be constant integral V1 to V2. And then what is left is 1 over V with the index of n times dV. And then let's continue. Constant integral V1 to V2. The integrand 1 over Vn can be rewritten to V with the index of negative n times dV. Okay, so now let's continue. Let's continue. All right, so copy constant. Can you perform this integration? V, the new index should be negative n plus 1. And then what is the coefficient? 1 over negative n plus 1. Okay, so this is what you should have learned in your calculus class. If you don't remember it, make sure you go back to your calculus class. All right, and then copy down the lower limit, v1, upper limit, v2. Okay, plug them in. Solution is constant multiplied by 1 over 1 minus n multiplied by v2, 1 minus n minus v1, 1 minus n. Okay, just plugging the upper limit and the lower limit. Okay, everything looks great because we have got rid of the integral sign. What we have left is multiplication, which is much easier for us to use. Okay, so now, but the downside is constant. What is the value of this constant? I need to find out the value of the constant in order for me to find out the value of W. So what is this constant? Let's recall. PVN is equal to constant. If that's equal to constant, that means the value will never change. So the value at the initial state must be equal to the value of the final state. I can apply this equation to the initial state and also to the final state. where subscript 1 means initial and subscript 2 means final. So now, can we actually rewrite constant from here? P1V1n is equal to constant. So now I can rewrite constant into P1V1n. Okay, so now let's continue. This becomes P1V1n multiplied by 1 over 1 minus n multiplied by V2, 1 minus n minus V1, 1 minus n. Okay, so let's continue with math. Okay, P1V1n over 1 minus n, combine the first two terms, and copy what is left, V2, 1 minus n minus V1, 1 minus n. Okay, and then expand right hand side, P1 V1n times V2 1 minus n over 1 minus n minus P1 V1n multiplied by V1 1 minus n divided by 1 minus n. Okay, so now we have expanded right hand side into two terms. Okay, so now let's continue. Okay, so what do you notice about the second term? Can I combine those two terms into single one? Yes, you can. So it's P1 V1n times V2 1 minus n over 1 minus n minus P1. If you combine them, what will it become? V1, and what is the new index? N plus 1 minus n. So the index will just be 1, P1 V1 over 1 minus n. Okay, so now let's continue. Can I do something about the first term? P1 V1n times V2 with the index of 1 minus n. Can I do something similar? Let's recall what we have right here. P1 V1n is equal to P2 V2n. Okay, so I'll just write it down here. Recall P1 V1n is equal to P2 V2n. So what I can do is to rewrite P1 V1n into P2 V2n because they're equal. So it becomes P2 V2n multiplied by V2 1 minus n divided by 1 minus n minus P1 V1 over 1 minus n. Okay, so now can I combine those two terms? Yes, you can. You just do the same thing. P2 times V2. What will be the new index? N plus 1 minus n, which is just 1, over 1 minus n minus P1 V1 over 1 minus n. So finally, what is our solution? W is equal to P2 V2 minus P1 V1 divided by 1 minus n. That is our final solution. So now, with this equation, it is much easier to find out the value of work because all you need is everything in the right hand side. P1 V1 you can easily measure their initial pressure and initial volume. P2 V2 you can also easily measure their final pressure and final volume. N is material property, which depends on what kind of gas you have. So everything is easy to find. And then after you find everything, you just plug them in into the right hand side. And then you can easily find out the value of work. So that is the second method, analytical method. The good thing about this method is we can actually find the equation to calculate the number of the work. the value of the work. The downside is we cannot visualize it like we did in the first method, which is the graphic method. Okay, so now just to summarize, summary, work is equal to, first of all, the equation is, okay, let me erase this quickly. Okay, so we always want to write down the original equation. The original equation is P times dV from V1 to V2. And then after that, you realize the equation we developed is P2 V2 minus P1 V1 over 1 minus N. This is absolutely true. Okay, however, sometimes we use a different one. What is that? Sometimes we use this one. Okay, let me change the color quickly. Sometimes we just use this one instead, even though we know they are equivalent. Sometimes we prefer to use the second choice, and I'll explain why later. P2, V2, and oh, sorry, okay, erase that, change the subscript. What we actually usually use is this one, P1, V1, N times V2, 1 minus N over 1 minus N minus P1 V1 over 1 minus N. So this solution is only an intermediate step in our derivation. However, we usually use this one. Why? Because if you take a look, if you use option number 1, how many unknowns do you have to find? P1, P2, V1, V2, and N. So in total, you have 5 unknowns. However, if you use the second option, even though the second option doesn't look as nice as the first one, it's longer, it's uglier. But if you take a look, let's count how many unknowns do you need in your option number 2. P1, V1, V2, N. That's it. You only have 4 unknowns. So that's why usually we prefer the second one, because it can make your calculation easier. You just only need to find 4 unknowns, then you're done. You just do the plug and chug, even though the equation looks longer and uglier. Okay, so what does that tell you? First impression is not always the correct impression. Okay, all right, so a few notes I want to say. First one is this equation we developed applies to both expansion and compression. Doesn't matter which one. And then second one, the system is gas. Okay, we need to make it clear. The system in our examples is always the gas. Okay, to finalize our class today, we do a very quick example. Very quick example. Find work W if pressure P is constant. Okay, how do we find work? So now we go back to the equation we just developed today. How many options do you have? You have 3 options. You can use the original one, integral PDV. You can use the very short one, very pretty one, or you can use the very long one. So which one do you actually use? So here's one thing I always suggest you do. If you don't know, always start from the basic, which is integral PDV from V1 to V2. Always start from the basic. Okay, so now let's take a look again. Pressure P in this example is constant. In other words, your integrand is constant. If your integrand is constant, what can you do? you can pull it out. So you can pull pressure out of it. What is left is integral dV from V1 to V2. So what is that? Your integrand is 1 now. So what is the solution? Volume from V1 to V2. And what is left? Pressure multiplied by V2 minus V1. And what is V2 minus V1? V2 is final volume minus V1, which is the initial volume. Usually we just call it the change of volume, delta V. Okay, so that is our example.